be to provide solutions to exam one, scoring adjustments, including the impact on overall grade, and an adjustment that was made to how your grades are weighted within web courses to more accurately to reflect your running average in the course and why that was done. First, the solutions to your exam. The exam was broken up into 4 parts. The first part was 3 questions related to chapter 1, followed by 3 questions related to chapter 2 concepts, followed by 3 questions related to chapter 3 concepts, followed by 4 questions with an increased focus on problem solving itself using the concepts in chapters 1 through 3. The first problem had to do with propagation of significant figures through the operations of division and addition. To accomplish that, you were told that you can calculate the density of a substance if you can compare known values of their mass and volume. You were then provided values of mass and volume for 2 substances and asked to combine or sum their densities. Object 1 has reported mass of 20.0 kilograms and a volume of 12.5 meters cubed. Object 2 has a reported mass of 0.035 kilograms and a reported volume of 1.0 meters cubed. We can find the density of both objects, noting the digit holding the significant figure in each case. So for object 1, the density would be 20.0 kilograms divided by 12.5 meters cubed. Each of those numbers has 3 significant figures. The operation is division. Therefore, I should keep 3 significant figures in my result since each of the inputs has 3 significant figures. When I do that division, I get a number of 1.6 on my calculator, so 1.60 would hold the significant figure digit place. For object 2, same process. In this case, each number contains 2 significant figures, so my results should be reported to 2 significant figures. This is a relatively easy operation as I'm dividing by 1, so I will get a result of 0.035 kilogram per meters cubed with the 5 holding this significant figure digit place. We were then asked to take these densities and add them. When you track significant figures through the operation of addition, you're tracking the digit that contains the significant figure. So 1.60, the 0 is the decimal place holding the significant figure. That's the second one to the right of the decimal place. Plus 0.035, the 5 is in the third decimal place. When we add 2 inputs, we will keep the digit that's closest to the decimal place on the right of the decimal place. That would be the second digit or where the 0 lies. So when I add this, I will get 1.635. The decimal place holding the significant figure would be where the 3 is. So rounding to that decimal place would be 1.64 kilograms per meter cubed, which was an answer choice. Question 2. Question 2 had to do with the conceptual understanding of the difference between the word accuracy and the word precision. Accuracy is a measure of how well a device reproduces the actual value on average of some measured quantity. In this case, we have devices that measure mass. Scale 1 measures masses of 24, 25, and 26, and we're told that this sample should have a known mass of 25 kilograms. So when we look at this sample of data and collect or create the average value, it would be 24 plus 25 plus 26 divided by 3, which would give us an average value of 25 kilograms, which happens to be equal to the reference value, meaning this scale is accurate. The uncertainty or the difference between reference and average is 0. Scale 2, same process. We get 25.2 kilograms. The reference value is 25 kilograms. There is a greater discrepancy between the average value and the reference value in this set of measured data. Therefore, scale 1 would be more accurately measuring that value than scale 2. Precision is how well a measuring device reproduces the same data for the same measurement. So that's a question of if you measure the same thing, how close are the values coming to each other? At scale one, I can see that each of these is plus minus one is the variance relative to the average, right? 24 is one below, 26 is one above. Scale two, all of these values lie within a range of values of 0.7. So my variance is somewhere between 0.3 and 0.4 maximum variances, depending on who I'm looking at relative to the average. Scale two is much more precise. It's providing much more reproducible data. It's simply not calibrated as well and is therefore less accurate. So the answer choice here would be scale one is more accurate, but less precise. Question three. This is simply a unit conversion. That was a chapter one learning objective that was covered in the PAL content. You're given a unit of speed in miles per hour and asked to represent that in meters per second. So we can do this through two conversion factors. First, we can deal with the hours in the denominator by multiplying by the conversion factor that says 1 hour equals 3,600 seconds. Put the hours up top, put the seconds in the denominator, and hours will cancel, and we'll be left with seconds in the denominator. And then we can also then multiply by a second conversion factor that deals with the miles, that puts the conversion factor that says 1,609 meters equals 1 mile. Put the meters up top, put the miles in the bottom. Miles will cancel with miles, and I will be left with units of meters per second. Run this through the calculator, 65 divided by 3,600. Take that result, multiply it by 1,609, and I should get 29 meters per second. Question four. This is now chapter two, conceptual stuff. Quiz two had things like this. This is graphical comprehension of how you can relate graphs of acceleration versus time to graphs of velocity versus time and graphs of position versus time. You're given the following acceleration versus time, which shows a period of time during which you had a constant positive acceleration. You then have answer choices of either position versus time or velocity versus time graphs, and you're effectively asked, do any of these correspond to what the motion described in this acceleration versus time graph would be depicting? Well, acceleration is equal to a change in velocity over a change in time. So then on a velocity versus time graph, the acceleration at any given point in time should reflect the slope of the graph. Since the acceleration is constant and positive, what that means is any velocity versus time graph that would correspond to this motion should have a constant positive slope. So I would expect some graph that could look like this, any of those would be possible, but I would need to have a constant positive slope. I look at my velocity versus time graph options, none of them do that. So velocity versus time graphs cannot be a correct answer given the answer choices that were provided. Similarly, velocity and position have a related type of relationship where velocity is equal to the change in position over the change in time. So in a position versus time graph, the velocity at any given time should be telling me the slope of the position versus time graph. Since the velocity will only ever increase at a constant rate, that tells me that my slope should only ever become increasingly more positive. If I start with a slope that is negative, so at the beginning here I have a downhill slope, then an increasingly positive slope would first get closer to flat, meaning less negative. So steep downhill becomes less steep downhill, becomes less steep downhill, which eventually becomes close to zero. That is a slope that is increasing from negative values towards zero. If I start with a slope that is close to zero or positive, that should only ever become more steeply positive. So close to zero, uphill, more steeply uphill, more steeply uphill. So that would then necessarily be a curve rather than a line, and it would be curving towards uphill from downhill. If I look at my options, the first position versus time does not do that. It has a slope of zero at all times. The second graph here does. It starts with a slope that is initially downhill and steep, becomes less steep, becomes zero, becomes positive, becomes more steeply positive. this graph is consistent with this graph, that would be my answer choice. Question 5. You have a velocity versus time graph, and you're asked to use it to determine the displacement within a certain time period. There are several PAL questions like this. There was a quiz 2 question similar to this. There's two ways you can do this. The easy way is just to understand that when you look at a velocity versus time graph, you can visually, graphically back out a displacement over a certain time period by calculating the area bounded between the graph and a velocity of 0 over the range of your time period. So in that case, that would make a shape that is a triangle. That triangle would have a base of 2 meters per second in height and or their base, and then a height of 3 seconds. 2 meters per second times 3 seconds would be 6 meters, but a triangle only takes up half of that area, right? 1/2 base times height. So I would get positive 3 meters. How do I get positive? This entire area is on the positive side of V equal to 0. So that would be the easy way to get plus 3 meters to be the displacement. You could also work this out using your equations. Your kinematic equations tell you that the displacement in a given amount of time should be equal to an initial velocity multiplied by that change in time plus 1/2 your constant acceleration, which we happen to have here, multiplied by the period of time squared. To use this, we'd have to first determine what that acceleration was. Acceleration is defined by a change in velocity over a change in time. In our case, we went from 2 to 0. That's a change in velocity of negative 2 meters per second. It happened in 3 seconds, so our constant acceleration was negative 2/3 of a meter per second squared. And then when we put that acceleration into this equation with 3 seconds where time goes and 2 meters per second for our initial velocity in this direction, we would get 2 meters per second times 3 seconds is 6 meters plus 1/2 times 2/3 of a meter per second squared times 3 seconds squared, which is 9 seconds squared, would end up being 6 minus 3 is positive 3 meters. So both ways we get the same answer, which is good. Positive 3 meters is how much this object displaced in that time. Question 6. You drive to the post office located 3 miles from your house. It takes you 15 minutes. You spend 5 minutes at the post office, and then you go back home. It takes you 30 minutes for the return trip. What is your average velocity during the full round trip 50-minute ordeal? This is just really, do you understand what displacement means and how it relates to velocity? Where did you start? Your house. Where did you end? Your house. So for the full trip, what was your displacement? Your displacement was 0. You began and ended at the same place. What is the definition of velocity? It's a displacement divided by a time. What is the displacement part of that? 0. What is the time part? 50. What's 0 divided by 50? 0. What was your average velocity? 0 miles per hour. All right. We're given a vector. We're shown an angle with respect to our axes. We're asked for the x component. The x component should be parallel to the x-axis. That would be the x component of vector A. We note that that makes a triangle, a right triangle specifically, with respect to the y-axis. We note that the leg of our triangle AX is not touching the angle. It is opposite the angle. Therefore, to calculate the magnitude of this leg, the x component, we would take A times the sine of theta, which is a rearrangement of what SO tells me in SOHCAHTOA. Sine of an angle equals the size of the opposite leg, the leg opposite the angle, divided by the hypotenuse. In this case, the vector A is the hypotenuse of the triangle that we have made, and the x component is the leg opposite the angle. So it would not be A cosine theta. That is not simply how you get x components. You use trigonometry correctly to get an x component relative to where the angle is placed within the right triangle that you end up making. In this case, based on where the angle was provided, that's a sine function. If we had placed the angle down here, then you would use A times the cosine of that angle. But we didn't put the angle down here, we put the angle up here. Okay, question 8. Which of the following represents the magnitude of vector C if vector C is equal to vector A plus vector B? I think this is almost identical to a quiz question on quiz 3 rather. Sorry, we're on quiz 3 stuff now. So graphical addition of vectors, they're already in a tip to tail arrangement, meaning vector A's tip is placed on the tail of vector B for us. We don't have to move anything around in our heads. So therefore, the sum of A plus B should be the vector that connects the tail of A to the tip of B. So C would lie here. The x component of C would be the sum of the x components of A and B, which is just from here to here. That's the going left to right from the tail of A to the tip of B. That's 6 units to the right. The y component of C would be from the tail of A to the tip of B along the y-axis. That would be -1 unit or 1 unit down. So the size of C, this is a right triangle. Pythagorean theorem tells me that cx squared plus cy squared, take the square root of that sum, is the size of vector C. 6 squared is 36, 1 squared is 1, 36 plus 1 is 37. The square root of 37 is the length of that hypotenuse. Question 9. 2 rocks are thrown from the top of a building. Rock A is thrown horizontally. So we have a picture, rock A, horizontal initial velocity. Rock B is thrown upward such that it can fall. So rock B is thrown upward so that it could fall along the side of the building. It's thrown with a very small initial velocity in comparison to rock A. Which stone lands first? So this is kind of a conceptual question. There's math involved. You can use math. There's math over here. I'll explain it conceptually. The initial vertical component of velocity of rock A was 0. It was thrown horizontally. It had no vertical initial velocity. It wasn't thrown up nor down. That means it was essentially from the vertical component, starting with an initial vertical component of velocity of nothing, and then accelerating downward due to free fall. By comparison, rock B had an initial vertical component of velocity. It was pointed upward and greater than 0. Therefore, before rock B can fall, it must first rise and come to a stop. That additional time will cause rock B to land after rock A, because rock B will not start its journey downward until it's at a greater height at a later point in time. Whereas rock A will simply fall from its initial height of vertical displacement equal to the height of the building. So conceptually, for those reasons, rock B will necessarily land after rock A, given that the land near the building is level, meaning they both start at the same height, both end at the same height. Albert jumps out of a tree into a trampoline. Upon impact, the trampoline depresses before springing Albert back into the air. At the very bottom of Albert's trajectory, when the trampoline is most depressed it will ever be, in which direction will Albert be accelerating? Well, I took the time to turn this into acceleration velocity and position versus time graphs. I even included for the fact that the changes in acceleration are not immediate. Meaning as soon as you make contact with the trampoline, you do not instantaneously become positively accelerating at a fixed value. Nonetheless, as you're about to learn in this section, the size of your acceleration will be equal to the size of your net force. The forces involved when you hit the trampoline will be a spring force upward and your gravitational force downward. You don't have to worry about forces. That wasn't part of this test. It's not necessary to get this question correct, but it is necessary to kind of get an idea for where these curves come from. In any case, to get this question correct, all we got to ask ourselves is, from a velocity standpoint, what should be happening at this point in time? Well, this is the lowest Albert will ever get. Before this point in time, Albert was traveling downward. After this point in time, Albert will be traveling upward. Albert's motion is kind of smooth. This is a rolling stop, similar to a pen when you throw it upwards and it instantaneously pauses at the top of its journey. This is a change in direction. The change in direction is from down to up. Necessarily, that must correspond to an upward acceleration. The velocity is getting more positive. So even though you're temporarily stopped, your acceleration is positive. And if you take the time to kind of analyze these graphs, you'll see that they do indeed correspond, that the positive acceleration corresponds to what's going on with the slope of the velocity versus time at this point in time when the velocity is instantaneously zero. Question 11. So where are we now? We're still dealing with chapter. No, we're in problem solving. So that last one was the first of the problem solving questions, I guess. A bullet is shot from the top of a cliff. So this is the first one that really involves a significant amount of math to get a correct answer. So we have a cliff, bullet is shot. It lands 500 meters away from the cliff face. So that's a horizontal component of displacement of the bullet during the 3 seconds of time for which it traveled. We're told that it lands with an impact velocity or an impact speed of 250 meters per second. So it's 250 meters per second. It's got to be going down and to the right, given my drawing, simply because I know that the bullet traveled to the right, so it must have some component of velocity pointed rightward, and I also know that it fell from a height, the top of the building, down to the ground, so it must have a vertical component of velocity pointed downward when it lands. All right, so with this information, I already know this part of this right triangle that is always formed when we decompose a vector into its components. I have enough information to determine the size of one of these parts, that being the horizontal component of velocity, for which I know, given the rules of projectile motion, that the horizontal component of velocity will be constant throughout the entire flight, meaning if I find it for any period of time or the whole period of time, I can apply it to any period of time. I can use the entire time period and my knowledge of the horizontal component of displacement and the total time that the bullet remained airborne to determine what this velocity was during that time period. That velocity would be the horizontal component of displacement divided by the amount of time the bullet was airborne, and it will be 166 and 2/3 meters per second. So I know this now, and I know this. That means I have enough information to know this, the vertical component of the bullet's velocity when it landed. That will be equal to, it's my choice to put the negative sign here. The square root in your calculator is agnostic about whether the result should be the negative or positive root. We place the negative because we know this will be going downward based on the situational awareness that the bullet fell. What I will do to get the size is Pythagorean theorem, where I'll take the hypotenuse squared minus the known leg squared, take the square root of that to get the unknown leg. That would be my v final y. My final velocity or final speed was 250 meters per second. The negative sign doesn't really matter, but it was down. But once I square it, that washes out. And I'm going to subtract from it the Vx squared. Vx was 166 and 2/3 meters per second. When I complete this process, I will get a final downward velocity of 186.336 meters per second. So now that I know the final vertical component of velocity of my bullet when it landed, I can use that with my knowledge of how much time it traveled for to back out what its initial vertical component of velocity must have been. I do that leveraging the fact that I know I have a constant vertical component of acceleration of negative g while I'm in projectile motion, as the object will be in free fall. And from that, I can say that the initial vertical component of velocity relative to that time period will be equal to the final vertical component of velocity during that time period minus the constant acceleration during the time period multiplied by change in time. That's just a rearrangement of one of the equations underneath the condition of constant acceleration at the top of your exam. Now I just put in what I know. I know that the final vertical component of velocity was negative 186.336 meters per second. From that, I will subtract negative 9.8 meters per second squared, since my constant acceleration is negative g, which I multiply by the 3 seconds of total time in free fall. From that, I get that the bullet would have been fired at a slightly smaller speed of 156.936 meters per second downward. And that speed increased due to downward acceleration throughout its journey. to the final downward velocity of 186.336 meters per second. Why do we have to do this? Because it asked the angle at which the bullet was fired. So that is an initial point in time. That's when the bullet left the gun, not when it landed. So we need to know about the components of velocity at that point in time. This is the vertical component of velocity at that time. This is the horizontal component of velocity at that time because it's the horizontal component of velocity at all points in time while the bullet was airborne. So now I have a triangle for the initial point in time where I have the x component at that time, the y component at that time, and I can, in this case, I want an angle, use the fact that opposite over adjacent is equal to the tangent of this angle. And that is the correct angle because all of my answer choice are relative to the horizontal. And this would end up being an angle of 43 degrees below horizontal. All right, question 12 was a relative velocity question. We talked about how to always get these right, identify your references, and then set them up such that if you're looking for a velocity of one thing in relation to another, you can always do that by a vector sum of velocity of thing one relative to a common reference plus velocity of the common reference relative to thing two. Right? And so you get this sandwich where y is the first of the first, f is the second of the second, which matches the ordering of the subscripts of the thing I want. In this case, those vectors are not aligned in the same sets of directions. The velocity of the conveyor belt relative to the floor is that way, as depicted here. The velocity of u relative to the conveyor belt is that way. And so the vector sum of those two, right, yb plus bf, in this case, I reverse the order, which you can do in addition, would be completed graphically by tail to tip. Tail of the first connected to tip of the second, when arranged this way, should be the vector sum, such that this would be the velocity of u relative to the floor. To get the magnitude of that velocity, I would simply complete Pythagorean theorem. Leg squared plus leg squared, square root of that sum is the hypotenuse. And this is, again, as was the case in one of your quizzes, a very common right triangle known as a 3, 4, 5 right triangle, where this was 3, this was 4, this was necessarily 5. You are traveling at 5 meters per second relative to the floor during the period of time that you are traveling at 3 meters per second to the right relative to a conveyor belt that is moving at 4 meters per second upward relative to the stationary floor. Last question. Soccer ball is kicked with an initial velocity of 17 meters per second from ground level. The ball remains airborne for 0.597 seconds before returning to the ground 10 meters away from where it was kicked. What is the maximum height of the ball relative to ground level as airborne? Well, you can use this information to draw a picture. Here's ground level. Here's where we kicked from. Here's where we returned to. Distance between them is 10 meters. Total time in the air is 0.597 seconds. We're interested in this change in height at the maximum vertical displacement. That will be in the middle. What we can get from the information we were told, since we know the object's in projectile motion this whole time, we therefore know that the horizontal component of velocity should be constant for that time period. Since we know the horizontal component of displacement and we know the total amount of time, we can use that to figure out what the size of that horizontal component of velocity was, and that would be 16.75 meters per second. That will be true at all points in time throughout this trajectory. We were also told the total velocity with which the ball was kicked. So we can again make a triangle where the ball was kicked with an initial velocity. We know that that velocity had a certain horizontal component. We know that those two numbers are not the same. 16.75 and 17 meters per second are different numbers, and therefore we must also have kicked it with some amount of vertical component of velocity. Using Pythagorean theorem, we can figure out the size of that vertical component of velocity. That's shown over here. Unknown leg will be equal to square root of hypotenuse squared minus known leg squared. Hypotenuse is the size of the vector. So 17 meters per second was our initial velocity. X component of that vector was 16.75. Square both of those, complete the subtraction, complete the square root, and you'll find that you must have kicked the ball with an initial vertical component of velocity that was 2.904 meters per second upward. Okay, we can figure out the maximum y component displacement with knowledge of what will be true about the y component of velocity at the maximum height. Necessarily at the maximum height, we will transition from the period of time where the ball travels upward to the period of time where the ball travels downward. So at that point in time, we must instantaneously have a vertical component of velocity equal to 0. With that knowledge, we have enough information to use one of our constant acceleration equations that relates the final velocity of an object to the initial velocity of an object, if provided a known constant acceleration in the same set of directions, and the displacement of an object. So we rearrange that to solve for the vertical component of displacement, given our known knowledge that the final vertical component of velocity will be 0, that the initial vertical component of velocity is 2.904 meters per second upward, and that the constant acceleration is negative g. Plugging those things in, 0, 2.904, negative 9.8, we get a negative over a negative, which is good because we should have displaced upward. And the math tells us that that vertical upward displacement should be 0.43 meters. We can check this with another one of the equations from the range and height. In this case, we would use the height equation for projectile motion when an object is launched from and lands back on the same level surface. To use that, we need knowledge of the initial velocity and the launch angle. We do not yet have the launch angle, but we could have easily gotten it back at this step. At this step, we knew the horizontal component of velocity with which the ball was kicked, and we knew the initial velocity. That's two parts of a right triangle. Launch angle lives between them. Therefore, that angle should be related through a cosine function, ca. Cosine of theta is equal to the size of an adjacent leg of a right triangle divided by the hypotenuse of the right triangle. In this case, the adjacent leg is the x component, the hypotenuse is the initial velocity. Move the cosine across, you get cosine to the negative first of that ratio, and that will turn out to tell you that you must have kicked the ball at a launch angle of 9.838 degrees. Okay, the height equation tells us that for a given launch velocity and given launch angle, that the maximum height attained should equal whatever this operation gives us. So initial velocity of 17 meters per second multiplied by the sine of 9.38 degrees. Take that result and square it, divide it by 2 times 9.8 meters per second squared, and you will indeed get 0.43 meters. This is good. Two different ways to solve the same problem give us the same answer. That must be the correct answer. All right, so that's a solution to every question on your first exam. Now for a little bit of the statistical analysis of how we did, what it means, what we're going to do. This is how we did as a group of 3 different sections of the class combined in aggregate. Unadjusted exam scores are down here. Each bin effectively relates to getting one more question right. So 0 is people who either did not take the test or got no questions correct. It's a little bit skewed upward because there's a number of people who did not take the exam. One question right would be 7.7% to 15.4, etc. The highest someone scored was getting 12 out of 13 correct. And so what we did with this is superimposed with this is the noise floor. So all of your questions had 5 answer choices. So statistically, if you just chose question answers at random, you should have had a 20% chance of getting any question correct. So your noise floor should have been centered at a 20%. Our average score was a 35. The standard deviation window actually butted right up to that noise floor and then extended out to a 50. What we then did, and this is something I commonly do, is we adjusted the meanings of these. So noise floor to me means no learning gain. No learning gain necessarily has to be at least an F. So the way your scaling adjustment was made is a grade of a 20 is scaled such that it would become equivalent to a grade of a 45, which is 5 points below what your syllabus says an F threshold grade is. Similarly, I took the highest grade attained and said that will be saturation of this testing instrument. So a 92.3 was adjusted such that it would become a grade of 100. The scaling adjustment is then linear between those 2 points, and it gives you a linear function that tells you how to take your unadjusted score and convert it into your adjusted score, which shows up here. So 92.3 would turn into 100, 84.6 should turn to a 94.1, etc. The grades up here are referenced to your syllabus grade scale, which tells us a grade above an 88 would be an A. So anything in this range is an A. Anything in this range is what the syllabus tells us is a B, C, D, F, etc. The grades reported to web courses have been adjusted as of this morning to reflect the adjusted exam scores rather than the unadjusted exam scores that the exam kicked out on its own. To visualize what was done a different way, this is the normal distribution of the unadjusted exam scores on exam one. And effectively what you can visualize is I took this, and if you visualize it as if it was an accordion, I pushed it this way until it was at a 45 with my left hand. I took this end of the distribution and I let my right hand slide over to 100. And in doing that kind of squeezing motion, if you picture this as an accordion, the gray curve was compressed and shifted over to become the black curve. The net effect of this adjustment on the course average in the class was such that before this grading adjustment, the overall class average grade distribution looked like this curve here, which would have been centered between a C and a D, and more or less compressed it, squeezed it over to the right, such that the course average is just below the threshold of a B. So between a B and a C, which is reasonably speaking where it should be. I would like to see us do a little bit better such that this shifts to the other side of the BC threshold. That is something that I will be working on my end, and ideally you will be working on your end as well. But big picture, for the most part, no one is in significant danger of failing the class. There's a minority of students who are in this D range who are within striking distance of a C. If we can take enough corrective action fast enough to shift everyone to the right through improved performance. One last note, I received a bunch of emails about an adjustment I made, and the fact that I received those emails is testament to why I make this adjustment now rather than later. You will not have a grade for your final exam until after you take your final exam, which will be the last thing you do in the course right before you receive your final grades in the course and they get entered to the registrar's office. If you let web courses do what it wants to do algorithmically to report a course average, then it needs to fill the fact that it's missing the 20% weighting that your final exam will eventually occupy. And so since it doesn't have any understanding for what the different grade categories are, and if there's any systematic bias in how people will perform in one category versus another, it fills that void by simply taking an exact proportion of all of the other remaining elements of the class and averaging them in those proportions to fill that 20% void. Well, that will only provide you an accurate reflection for how you're actually doing in the class if it is likely that every single category of the class will have the same graded average. And for example, it won't. Since we're human and we know what the different categories are for, we know that, for example, attendance, you can either attend or not, but that's not going to be correlated necessarily to exam performance. Same thing with completing discussion sections, right? That's based on completion. If you do it, you get a perfect grade. It's unlikely that you're going to match that on a graded assessment. So, to more accurately reflect what your grade will be after taking the final, rather than doing what WebCourses does automatically, what I like to do early in the semester, which is what I just did now, is instead of allowing WebCourses to take the full composite of your running average and fill in that missing 20% weight of your grade, I fill in that missing 20% of your grade with the midterm average, which only happened now because I only just now got your midterm averages or first grades. And so, in doing so, since we tend to score lower on the midterm than the average of the other components of the course, many of you have noticed that your grade dropped. That is good in a way because you know it now rather than having that happen after you take the final exam and being surprised then. So at this point, you should have a much more accurate depiction of how you are doing in the course if you are to continue performing in each element of the course in the exact same manner that you are currently achieving grades. With the assumption being that midterm exams should be the best possible reflection of final exam performance.